Hi there, this is the fifth video on the June 2005 OCR mechanics paper. This one can be a bit of a tricky one, so let's have a quick look at it. So here we have a uniform rod AB, which is 60 centimeters long, and it has a weight of 15 newtons. Now it said it was uniform, so we know this is going to be perfectly in the middle, and it's being held in position at this end here, A, and the other end of it, B, is being held in position by a piece of string that's 80 centimeters long from this horizontal distance here. And we know we've got a right angle here, which is going to be quite important later, and this rod is in complete equilibrium. Okay. And what we want to find out is the tension in the string, so this tension here. Okay, so there's a number of things we can do, but primarily because this is a 2D object with forces on it, there's going to be some turning moments involved as well as the forces. Okay, so let's go straight into this. I'm going to draw myself a very simplistic diagram though. So here is my rod. Okay, here. Now on this rod there is a tension in the string right here, which I don't know yet. Okay, and this is at right angles to this rod here, which is very important. Okay, and then I've got a fixed point here, A, so there's a pivot point here, and I know that the weight of this is 15 newtons. Oh, 15 newtons. Okay. So that's meant to be horizontally down. It looks a little bit skewed on the camera for some reason, so that's meant to be straight down. Okay. Now, I want to be able to take moments from A so that I can find what this tension is. Okay, so I know that this distance here is halfway to this distance here, and this whole thing is 60 centimeters. So from here to here is 30 centimeters, and then from here to here is 30 centimeters. Now, for a moment, I know that turning points are caused by a force multiplied by their perpendicular distance to a pivot point. Okay, and I can skew this round to make it horizontal for fur. So if this helps you, we can spin our paper around a little bit, and I've got a perpendicular distance here. I now just want a perpendicular distance from this point here. Okay, and I can see that this one is going to counteract the weight. So let's put in a little dotted line down here. So I'm going to want this angle here. Okay, and this is the trick to it. Okay, so I need that angle. So, what information do we have? Okay, so we've got length, so now I can draw some separate force diagrams if I need to. So, I've got a triangle that looks a bit like this. Okay, I'm just going to put in my horizontal bits here. So I've got angles here, here, and a right angle. Now, what I want to know is this angle here So that way I'll know no, sorry, beg your pardon, I don't want that. If I can find this angle here, I will know that this angle here is. Okay, so I know this is how long? This is 80 centimeters, and this is 60 centimeters. So let's work out what this angle is. So I know an opposite and adjacent, so tan beta is equal to the opposite over the adjacent, so 80 over 60. So using inverse tan, beta is 53.13 degrees. So I've now got an angle from the horizontal to this line of action here. Okay, so looking back on this diagram, from this line of angle here, I know this angle. So I hope that's clear there. Okay, and for part 2, we need to have a quick look at this question. So, we're being asked to find the magnitude of the force acting at point A. Okay, now here is where we can start to use Newton's laws. And we don't have to necessarily worry quite so much about moments here. So, if I now treat my our object as one solid particle. Okay, there's a force going in this direction, and that is our tension in the string. Okay, and then there's a weight going down, and these values are 15 newtons, and what we previously calculated before, 4.5 newtons. Okay, so I'm just going to add a little helping guides along here. Okay, now I know that this angle here is our original beta value, which was 53.13. So at the moment, based on just these forces, it's clearly out of equilibrium. It's especially obvious in this direction. So we can model the resultant force as two forces acting in both the y direction, Fy, and in the x direction, Fx. Okay, now in reality this will be one force, but once we know its components, F and in the y and x direction, we can then find what its single force is and in what direction. Okay, so based on this we're going to resolve vertically upwards. So Fy plus 4.5 cosine 53.13 will be equal to 15. So after you rearrange and solve that, you should find that the force in the y direction is 12.05 newtons. We'll do the same in the horizontal direction. And again, I'm going to go in the direction of the force that I know it's going to be in. So Fx is equal to 4.5 sine 53.13. And you should find Fx be somewhere around the lines of 3.92 newtons. Okay, now I can draw a little force diagram for these forces to resolve it as one big force. So it goes to the right, it goes to the right at 3.92 newtons, and it goes up 12.05 newtons. So here is our resultant force, and I can use Pythagoras here. So 3.92 squared plus 12.05 squared, all square rooted, will give us the resultant force, or the magnitude, and we should find that to be 12.67 newtons. Okay, and we want its angle of direction from the horizontal. So we can now use tan alpha equals opposite over adjacent. So that's 12.05 over 3.92. So using inverse tan, we should get a value of about 72 degrees. Okay, and that's our job done for question 5.